Okay, so number 21 on your POGO states that, gosh, I got to find a pencil or a pen. Does anybody see my marker? There it is. I got it. Okay, so on number 21, you have an example that deals with sickle cell anemia. It says what? 9% of the population have that recessive disorder. So that's telling you, you guys, that 9% of that population have little s, right? And it's asking you that first question, the frequency of the recessive allele, which is Q. So this is kind of what we're after for that first question. And we know something. P plus Q equals 1. Okay? So all we have to do is find Q. Well, we know Q kind of in a way, because we have this other equation that says P squared plus 2PQ plus Q squared equals 1. So what I can do is I can look at Q because I already have Q squared. And we know that 9% is Q squared. So that means that Q squared equals 9%. And if I write 9% as a decimal, it's 0.09. Now, the question doesn't ask you for Q squared. It asks you for Q. So if I take the square root of Q squared, I will end up with Q, which is the recessive allele frequency. What is Q squared? What is the square root of 0.09? Is it 0.3? Okay, so 0.3 equals Q. So 0.3 is the answer for letter A. Now, if I know Q, who do I automatically already know? P plus Q equals 1, and we know Q is 0.3, right? So that means P must equal 0.7. So we automatically know the next one, just using our first equation, P plus Q equaling 1. Now the next one, it says C, the frequency of the homozygous dominant individuals in the African population. So now it's asking for this right here, P squared. It's saying how many of those individuals are big S, big S. Big S is another way of saying P squared. Do I know P? Yeah, P is 0.7. So that's like saying 0.7 times 0.7, right? Okay. We know that is going to give us P squared. So what's 0.7 times 0.7? 0.49. Okay. So 0.49. Ooh, that's a terrible 0.49. So 0.49 is the probability of individuals in that population that will be P squared, otherwise known as big S, big S. Okay? That was C. So D, the frequency of heterozygous individuals in the African population. So let's just get a new screen here. We know that heterozygosity is referring to 2PQ, right? So do I know P? What's P? 0.7. What's Q? What is it, 0.3? So we know those two. Great. So that's PQ, but I could also be QP, right? So I have to also say, okay, I could be 0.3 multiplied by 0.7 as well. That's why we have the 2PQ. Okay, you can multiply them and then add them like I'm about to, or you can just multiply P times Q and then times that by 2. Okay, don't forget your order of operations, all that good stuff. Okay, so after you multiply this out, that's 0.21, 0.21. What's 0.21 times 0.21? Help me out. That's 0.42. Oh, I added. Sorry. Whoa, I almost did that wrong, didn't I? So that's 0.42, right? Okay. So 0.42. Ooh. Come on now. So 0.42. Yes, you could do it the other way too. I'm just showing you that this is saying, okay, this is PQ or QP. Okay. You can put it either way. That's why you have to multiply it by 2. Okay? So 0.42 is the number of individuals that are PQ or big S, little s in a population. You guys get that? Okay. And then the last one. Based on this analysis, is the African population in the Hardi Weinberg equilibrium? Justify your answer. So, do I know that based on just this information? Not really. I'd have to have another generation to compare it to, right? And so if I did have another generation, which the problem does give you later on, that I compared this to, and then I got a shift in the P and Q. Let's say P the next time was 0.6. Then we know that the Hardi Weinberg does not hold true because something must have happened to disrupt it. If it was, let's say, 0.7 again, then I'd say Hardi Weinberg is being demonstrated. Remember, it's very rare in a natural condition to actually see the Hardi Weinberg stability play out. But we can use it to measure allele frequency differences to show microevolution. Okay? We get that? This one has to be crystal clear. Tomorrow I'm going to have you guys taste some PTC test strips, and we'll do a population count for us, just like that problem in your lab. So we'll do a real population experiment with our own class tomorrow. Okay? Yep. It's PTC.